Medical consensus has long associated metabolic syndrome with a chronic, low-grade, and static state of inflammation. The traditional model focuses on adipose tissue, assuming that fat cells continuously secrete pro-inflammatory cytokines to maintain a steady simmer of biological stress over years. High-frequency blood sampling reveals a different environment. Instead of a stable baseline, subclinical inflammation fluctuates on a minute-to-minute basis. Circulating monocytes drive this rapid volatility. Their behavior responds to specific environmental inputs, beginning with sleep architecture. A second factor is dietary, specifically the acute glycemic spikes triggered by heavy carbohydrate loads. These findings suggest everyday, non-pathogenic stressors bypass adipose tissue to directly command the innate immune system. Subclinical inflammation operates as an active phenotype, continuously rebuilt by daily lifestyle choices. The monocyte population operates as a diverse fleet, categorized by specific surface receptors. We map this fleet using flow cytometry. The y-axis tracks CD14 for detecting bacterial lipopolysaccharides. The x-axis tracks CD16, an immune signaling receptor. In healthy blood, a large cluster populates the top left quadrant. These are classical monocytes, expressing high levels of CD14 but lacking CD16. Classical monocytes are routine patrolling phagocytes that clear debris and maintain vascular order. A smaller cluster populates the top right quadrant. These intermediate monocytes express both receptors and handle antigen presentation. Finally, a third cluster appears in the bottom right quadrant. These non-classical monocytes have a unique low CD14, high CD16 signature. Non-classical monocytes specialize in patrolling the vascular endothelium, where they are uniquely capable of massive pro-inflammatory cytokine output. The circulating ratio of these three specific subclasses dictates the baseline volatility of a patient's immune system. A cohort study of 237 individuals tracked these ratios alongside objective lifestyle metrics. Subjects were categorized by body mass index and wore actigraph accelerometers for 7 straight days to map their sleep efficiency. This scatter plot shows total sleep efficiency. The data indicates the obese cohort experienced a significant drop in efficiency compared to the lean group. The adjacent chart tracks late after sleep onset, showing decreased efficiency was driven by frequent periods of wakefulness. Their sleep architecture was highly fragmented. When overlaying this data with flow cytometry results, the population of routine classical monocytes decreases as fragmentation rises. Simultaneously, the population of pro-inflammatory non-classical monocytes surges. A Pearson correlation analysis linked this specific monocyte shift to spikes in 9 distinct systemic inflammatory biomarkers, including TNF-alpha. Because obesity correlates with both higher BMI and worse sleep, researchers had to isolate the trigger. Mediation analysis proved that sleep disruption drives these monocyte levels independently of a patient's body mass index. To confirm this, researchers subjected 5 healthy, lean individuals to a strict 24-hour total sleep deprivation protocol. After 24 hours awake, non-classical monocyte levels spiked immediately. These levels reverted to baseline only after the subjects obtained 2 full days of recovery sleep. Chronic sleep fragmentation acts as a primary biological lever, shifting the immune fleet toward a reactive, inflammatory baseline before diet is considered. While sleep architecture establishes the baseline state, macronutrients exert acute control over immune behavior. A crossover study examined this by tracking monocyte responses in a cohort of healthy weight and overweight children. Subjects consumed 2 contrasting liquid meals, a high-carbohydrate maltodextrin beverage and a zero-carbohydrate egg-based beverage. This bar graph shows that 2 hours after the carbohydrate beverage, both groups experienced elevated plasma glucose compared to the egg condition. This chart tracks the corresponding spike in insulin production required to handle that sudden glycemic load. A massive glycemic spike is an established pro-inflammatory event. Physiologically, we would expect to see an increase in inflammatory immune cells patrolling the blood. This graph tracks TLR4, the primary pro-inflammatory receptor on monocytes. Instead of an increase, the data shows a significant drop in TLR4-positive non-classical monocytes. This drop occurred specifically in the overweight and obese cohort following carbohydrate ingestion, localizing to the classical and non-classical subsets. Researchers discovered a strict inverse correlation. The higher the plasma glucose spiked, the more inflammatory monocytes vanished from circulation. An acute sugar load does not destroy these cells, which raises a question. Where did an entire fleet of primed immune cells suddenly go? Researchers propose that this disappearance represents a targeted cellular migration out of the blood. An acute hyperglycemic spike alters the intestinal epithelium, increasing its permeability. This spike triggers a localized generation of reactive oxygen species, causing acute oxidative stress at the gut barrier. Bacterial endotoxins leak through the weakened barrier into the bloodstream, a process known as metabolic endotoxemia. These leaked endotoxins act as a homing beacon for circulating non-classical monocytes carrying TLR4 receptors. Detecting these toxins, a primed monocyte halts and tethers itself to the blood vessel's inner wall. The monocyte then squeezes between endothelial cells, exiting the bloodstream to infiltrate gut tissue. Acute glycemic loads deploy inflammatory cells out of the blood and directly into vulnerable organ tissues, initiating a localized immune response. To understand subclinical inflammation, we must combine these environmental vectors into a unified model. Chronic sleep fragmentation acts as the factory setting, overproducing the reactive non-classical phenotype and raising baseline immune tension. Layering acute glycemic loads acts as a deployment mechanism, driving those primed cells into tissues. These two vectors collaborate to maintain the biological damage of metabolic syndrome. Addressing obesity-related comorbidities requires moving beyond counting calories to stabilizing the behavior of the innate immune system. Achieving glycemic stability and restoring deep sleep architecture provides a direct, real-time method for re-engineering the circulating immune profile.